In this video, we'll examine the average atomic masses of elements, how they're calculated, and how the relative proportion of the different isotopes affect the mass. But let's start by reviewing the three subatomic particles. The proton has a positive charge, and its mass in atomic mass units, or AMUs, is 1.0073. The neutron has no charge, and its mass is 1.0087. It's slightly larger than the proton. The electron has a negative charge, and compared to the proton and the neutron, its mass is so small, we're going to say that it's negligible or zero. But really, it does have a very small mass of 5.486 times 10 to the negative 4th AMUs. In this video, we're going to say that a proton has a mass of 1 AMU, a neutron has a mass of 1 AMU, and the electron has no mass. Let's review atomic structure. The little red dot here in the middle is the nucleus, and inside the nucleus we would find protons and the neutrons. Those are the two particles that have mass, and they're all inside a nucleus that has a diameter of about 10 to the negative 4th angstroms. Outside of the nucleus, in this area that's all purpled and squiggled, is called the electron cloud. And the diameter of the electron cloud is 1.5 angstroms. So most of the volume of an atom is the electron cloud. Now this is interesting. These numbers really aren't important for us right now, but what really is happening here is most of the mass of the atom is in a tiny space, and most of the volume has no mass. So if an atom were a football stadium, the nucleus would be the size of a marble, and the rest of the stadium would be the electron cloud. That makes our nucleus very dense. And inside that nucleus, there are protons and there are neutrons. And the protons have a positive charge and the neutrons have no charge. So the nucleus has a positive charge. And in that tiny space is where all of the mass of the atom is located. In that electron cloud, almost the entire volume is there, but virtually no mass. Now, atomic number, its symbol is a capital Z, is the number of protons in the nucleus. It will never change for an element. So the number of protons in the nucleus will always remain the same if it's the same element. The mass number, with the symbol A, is the number of protons and neutrons. Remember, the proton and neutrons are the subatomic particles that have mass. So if we sum their numbers together, we come up with the mass number. Let's look at an atom of carbon. It has an atomic number of 6, so it has 6 protons. It has a mass number of 12, so 6 protons plus 6 neutrons would give it a mass number of 12. And in this video, we're only going to talk about atoms which have no charge. So the number of positive particles, the protons, will equal the number of negative particles, the electrons, so the atom has no overall charge. So we're going to write the superscript number here will be our mass number, again, number of protons and neutrons, and then our subscript is going to be our atomic number, which is our number of protons. If we take our mass number and subtract from it the atomic number, we'll get the number of neutrons. So mass number minus atomic number equals our number of neutrons. Now let's look at another form of carbon. Here its mass number is 14, and it's carbon, so its atomic number is 6. It has 6 protons, but our mass number is different. We must have a different number of neutrons. So using our little formula over here, the number of protons and neutrons equals 14, minus our number of protons leaves us with 8, and that's how many neutrons are in that form of carbon. Let's look at another element. Let's look at boron. It has atomic number 5, And this form of boron has a mass number of 10. So the mass number minus the atomic number would lead us to realize that this form of boron has 5 neutrons. We might write it as B-10 and say boron 10. It's a little redundant to have to write the 5 because if it's boron, it's atomic number 5. Here's another form of boron. Its mass number is 11 and its atomic number is 5. Again, 5 protons, but the mass number is 1 AMU larger. So it must have 1 more neutron than this form of boron. So 11 minus 5 gives us 6 neutrons for boron 11. Well, boron 10 and boron 11 are 2 forms of the same element, and they're called isotopes of boron. Isotopes have the same number of protons. In other words, they have the same atomic number, but they have different masses. A different mass number is resulting from having a different number of neutrons. Now let's look at our periodic table. Above the symbol for boron is the atomic number. So boron has 5 protons. That atomic number is always your number of protons in the nucleus. This number below the symbol, it doesn't look like the mass number 10 or 11 that we were just talking about. Well, most elements are a mixture of isotopes. But again, our mass numbers were 10 and 11, so I was thinking that maybe this would be an average of the 2 isotopes. But that would give us 10.5. The average of 10 and 11 would give us 10.5, when actually this number here is 10.81. Well, this is what we're calling the atomic mass, and it is an average of all the isotopes, but it is a weighted average. So because this number is closer to 11 than it is to 10, we can assume that in nature, naturally occurring boron, there's a larger abundance of boron 11 than there is of boron 10. So our atomic mass is a weighted average of all the naturally occurring isotopes of the element. Now let's learn how to do a calculation with this information. So here are 2 isotopes of boron, boron 10 and boron 11, and here are the atomic masses, 10.01 and 11.01. And over here is our percent abundance. And just like we thought in the last slide, we really thought that there was probably more boron 11, and indeed there is. The relative abundance of boron 11 is 80.1%. Boron 10 is the other 19.9%. If we would like to calculate the atomic mass of boron, how we do that is we take one of the isotopes of boron, get what we call a relative abundance by just dividing the percent abundance by 100. So we have a relative abundance of 0.199, and we're going to multiply that by the atomic mass, 10.01. Then we're going to take the other form of boron, the other isotope, the one that's heavier and that's more abundant. We'll take the relative abundance by dividing our percent abundance by 100. We'll multiply it by its atomic mass, 11.01. These results that we get by multiplying relative abundance times the atomic mass will then be added together. So 1.99 out of the mass comes from boron 10, 8.82 atomic mass units come from the boron 11. We sum them together and we get the average atomic mass of 10.81 AMU for boron. So in conclusion, all the different isotopes of an element can be summed together, and we will take their weighted average of all the naturally occurring isotopes to give us our atomic mass that we find on the periodic table.